So continuing on with our discussion of the effective inside diameter of the expansion joint. Now, on an untied expansion joint, this is very critical that you specify this inside diameter. Again, the program will apply a force on either end of the joint and include it with the pressure analysis, and that force is equal to the effective inside diameter times the line pressure. You have to specify that effective joint diameter when it's untied. If you're building a simple model by hand and it's a tied joint, some people just don't specify the effective inside diameter and there's no pressure thrust applied. That way, that pressure thrust is not part of the analysis and you're assuming that the tie rods are going to carry the load anyway. When you use the expansion joint modeler in Caesar 2, the automatic modeler, the program will always add that effective inside diameter because it always generates the tie rods to carry the pressure thrust. So this might be a little trick that you have when you're doing simple models by hand. If you want to do an untied, you better be specifying the effective joint diameter. If it's tied joint and you want to simplify it, don't specify it and you will not see that pressure thrust in your analysis. Now, in the catalog, you will find this value, this effective inside diameter. Now, in the Senior Flexonics Pathway catalog, they don't list effective diameter, they list effective area. So here we see that for this 10-inch, 50-pound Senior Flexonics Pathway joint, the effective area is 109 square inches. In Caesar 2, we ask for the effective diameter. Take the area divided by pi, square root of that times 2 is our diameter. Area equals pi r squared. Right? So the diameter can be taken from that equation. So 11.781 inches is the effective diameter of that expansion joint. So we got our effective length, we have our effective area. Now we have to collect the stiffnesses from a catalog. I kind of got my eye on this 50-pound 12 convolution joint now. What is the axial spring rate? What is the lateral spring rate of this joint? What is the angular spring rate? If we know the axial spring rate, 689 pounds per inch, you can use an equation to calculate the lateral stiffness. The lateral stiffness is 3/2 times the effective diameter squared times the axial stiffness divided by the overall flexible length squared. So if I know that my axial stiffness is 689 and I know what my effective diameter is, if my length is, I can plug in these terms and there is my lateral stiffness, 1301. And yeah, 1301. So these are related to each other by the effective area or effective diameter and the flexible length of the joint. Now, there's also an equation for the bending term. The bending of the expansion joint is related to the axial stiffness and the effective area or effective diameter squared. Now, you might be using Caesar 2 where you're not specifying effective diameter. So if you don't specify effective diameter, how is Caesar 2 going to generate this term? Well, the program will instead use a relationship between the effective area or effective diameter and the lateral stiffness. So I can plug in my lateral term here, solving for the effective area, and plug that into this term, and now I have my bending stiffness as a function of the length of the joint, flexible length, and the lateral stiffness. Now, in Caesar 2, we would request that you only enter the lateral stiffness because the program will use this equation to calculate the bending stiffness. Now, we say you do that for metallic joints. Rubber joints do not have the same beam stiffness relationship. So if it's a rubber joint, I would say specify lateral and bending terms completely. We'll talk about in a second why we suggest you leave the bending stiffness blank. If you leave it blank, you better have the right flexible length because it's a function of that length. That's what you entered in Caesar 2 for the length of the element, and you enter this value, the program then calculate that bending stiffness. So here's that bending stiffness term. Since you typed in the lateral stiffness and the flexible length, you can leave that value blank in Caesar 2. Again, what am I talking about? It's this term right here that I'm leaving it blank. If you leave this blank, the program will use that stiffness there, and this length here, and this effective diameter in order to calculate the term. If you leave it blank, the program will give you this warning. Say, hey, you left it blank. So we're going to calculate it based on the other terms that you do specify. So what would happen in this model here? The bending stiffness is pi divided by 540 plus the lateral stiffness term, 1301. We calculated that in the previous screen, times the effective length or the flexible length squared. And I get 834 inch-pounds per degree. Now, there's 834. I go back to the catalog and look what the catalog lists. 209 as my angular spring rate. Why do we see that different value? Well, it turns out that many catalogs, this one is one of them, that show bending flexibility rather than bending stiffness. We're a beam program here. We take an element, a beam, a flexible beam, an expansion joint, and we need this bending stiffness in order to use in Caesar 2. But a lot of catalogs still show bending flexibility. What is a bending flexibility? You might have seen this earlier in a discussion on the guided cantilever approach, the stiffness of a cantilever, if you allow it to rotate at the end. When we talk about a stiffness model, we want just the pure stiffness of bending, some angle rotation, without allowing any deflection of that end. That would be a bending stiffness. If I put a bending moment on the free end of a cantilever and allow it to deflect as well as rotate, that's what we'll call bending flexibility. It turns out that if I put a certain bending moment on the end of that beam, and I look at it in terms of bending flexibility, it has a value of 209 inch-pounds per degree. If I do not allow the end to displace, it's 4 times larger, 834. So the general relationship in this point of view between flexibility and stiffness is a factor of 4. So we got to make sure we get the right number, or you don't specify it at all and let the program enter it for you. Here's an example of that same little test. Here we have an expansion joint of a length of a little over 10.5 inches. Here's my stiffness, my axial, transverse, torsion, and effective ID. What's in play here is its length, torsional stiffness, and effective ID. Now, I'm putting kind of a strange model here together. I'm adding a snubber in the Y direction. This is a snubber. It's a restraint that you can turn on and off for different load cases. And I'm putting a rotation at node 20 of 1 degree as a displacement set. And I'm going to see the difference in the load that I get on the restraints when I have the snubber out of the system, that'd be a bending flexibility, and when I have it in the system, that'd be a bending stiffness. And compare those numbers. Here I'm looking at the end node 20. I have 2 models here. The first one is free end displacement, and the second one is displacement control. So the first term is the bending flexibility, the second term is bending stiffness. And we see here that when I allow the end to deflect, it drops down 9/100ths of an inch, and there's my 1 degree rotation. The load I get is 208 inch-pounds per degree. When I hold it from moving down as I rotate the end, there's still at 1 degree rotation. It doesn't move at all, but now I get 834.47 inch-pounds per degree. The ratio of these two numbers is 4. We have to be sure we use the right number in Caesar 2, whether it's a catalog value or not. Now, again, many catalogs show a bending flexibility. If I model my system like this, where I go from one end of the joint, 10, to 20, but I stop at the midpoint with rigid elements at either end, and I put my stiffnesses right here, this is what we call a zero-length expansion joint. There is no length between 15 and 16, but they are 2 ends of that element. They are at the same point in space, but they're related by these stiffnesses. Now here, I'm typing in my bending stiffness, 209. And when I run this model, it works the same way. I get the same numbers that we saw earlier. So again, a lot of these catalogs still assume that a user of these data will model their expansion joint not as a finite length joint, but as a zero length joint right in the middle of the entire joint. So keep an eye on that term, use it properly. And again, this is one reason why I would suggest not specifying the bending stiffness, but then you have to specify the proper effective ID and also the proper lateral stiffness and length. So yeah, we get the same numbers whether we're using the flexible length of 10 inches or just going right to the center point. In our next segment, we'll talk about the remaining terms that are required for this expansion joint.